Module 30, Key Concepts of Statistics and Statistical Pitfalls to Avoid. Section number 1, Key Concepts of Statistics. This is the final module of the entire course, and I hope you enjoyed thoroughly, and all congratulations for coming all this way long. And this is very important module. This is like a take home message. What is actually the summary of the entire course and the most important things that you should be wary of while performing the statistics or while reading the scientific papers on the statistical significance. The key concepts is that the first and foremost thing is that there are so many statistical terms that are also used in real life, and the meanings in statistics is quite different. So if you think that those terms in statistics means exactly like the everyday language or the dictionary meaning, that is wrong. Some examples are significant, experiment, or variable, or confidence, or certainty, or confounding, error, hypothesis, model, normal, precision, accuracy, robustness. So these words have a different set of meaning in the everyday life, while in statistics the meaning is entirely different. So don't get confused about this meaning. So if you are unsure, go back to my earlier modules and find out the exact meanings of, for example, the experiment. What does that experiment means? Very important concept in statistics is GIG or GIGO principle. That is nothing but garbage in, garbage out. So if you are putting the garbage, and whatever the statistics that you are doing will not rectify the bad quality data. So the first and foremost thing before even doing the statistics is to generate high quality data. So any kind of statistical test cannot suffice it. So raw data is very important. Fancy statistical test cannot compensate the data quality. So don't merely look at the summary, that is average plus or minus standard deviation, but look at the raw data. So that is very important. The raw data is extremely important. So I suggest you to go with the scatter plot and the box and whisker rather than simply plotting, the mean plus or minus, like plunger, dynamite plunger plot. That is not really, interesting or convey any meaningful inferences. So beware of very large sample, because it's very easy to get an extremely low p-value with extremely large values, large samples. Beware of small samples as well, because statistical power of the test would be very low. So inferences would not be conclusive with the small sample. So you just need at the right size of the sample. So I've already told you how to calculate the minimum required sample size using the equation. You can go back and check it. Next important concept is that do not remove the outliers subjectively, because human tendency is that we can actually easily see that the shapes, we can actually detect the clusters and shapes and patterns, but we are not really good at detecting the randomness. So sometimes outliers are the most interesting part of the data, and many Nobel Prize winners have worked on the outlier data, not the normal data. So outliers are very interesting as well. Beware of multiple comparisons. Multiple pairwise t-test without doing Bonferroni adjustment is wrong. Multiple tests like parametric and non-parametric, and choosing the one that produces the lowest p-value is absolutely wrong practice that many scientists are still doing that, even if they do that. So even if they know that it's wrong, so it's deliberate malpractice. Automatic variable selection in multiple regression. So if you're asking the computer to do this selection of the variable, that is wrong unless you rectify that mistake by calculating the weighted p-value, adjusted p-value. Correctly interpret the statistical analysis. All analysis and significance level must be planned as part of the experimental design. Before collecting the data, you have to plan every single thing that you are going to do beforehand. All the planned analysis must be conducted and reported. So this is two of the important things that many of the scientists totally miss. So these are very pivotal rules that are widely broken across the sciences, so that you have to be very careful about it. So if you are planning to do some test, it has to be part of your scientific experimental design, and whatever you have included in your experimental design, you have to perform actually and report the data. And you cannot do something else, and do that. So that all will become part of the multiple comparison, and the p-value would be because of the false positive. You have to be beware of harking. What is that? Hypothesizing after the results are known, also known as double dipping. And also the changing the objectives of the PhD or MPhil or MSc dissertation after getting the results is also a form of harking. So you have to be very careful about it. Beware of the studies that don't truly test a hypothesis. So you have to actually test a hypothesis, right? So there are so many studies that really don't test the hypothesis, or the hypothesis is like unbreakable, that is beyond the falsification of the pauper. So many investigators are dogmatic and highly opinionated. They strongly believe in their hypothesis such that no data could be able to disprove such vampirical hypothesis, unable to be killed by the evidence. So such a hypothesis is called vampirical because it's nothing can destroy it, especially used for the pseudoscience. So not really in the science premises, but in pseudoscience this is very, very common, especially in alternative medicine. So this is the case with pseudoscience, and read about philosophical burden of proof exploit as well as Russell's teacup. So if you say that there is a teacup in between Mars and Jupiter that is circulating around the revolving around the sun, how can you disprove that kind of the hypothesis that is actually put forth by Bertrand Russell, that is the English philosopher, long time back. Another important things are the takeaway messages are statistically significant does not mean scientifically significant. So many people think that statistically significant means that, oh, this is really scientifically significant. That is incorrect. Statistically not significant does not mean scientifically not significant as well. So this is vice versa of the first argument. Confidence intervals are more important than the p-values. So a best practice is to report both the confidence interval and the p-value. So if you simply report the p-value, that is highly improper, because the p-values is extremely dependent upon the sample size. Very easy to get a low p-value by astronomical sample size. P-value less than 0.05 doesn't prove alternative hypothesis, as threshold is mere arbitrary and conventional. 0.05 threshold is just an arbitrary one. Effect size is more important, so as exact p-value and 95% CI. All these are extremely important. What is the effect size? What is actually the difference? And what is basically the exact p-value rather than p-value less than 0.05. It could be 0.049, which is very borderline case. So still less than 0.05 makes no sense in that such situations. Concepts of statistical significance is designed for quick and unambiguous decision making. There really is not much difference between p is equal to 0.045 and p is equal to 0.055, very near to the borderline. So there is not much thing. So it is just for a convenient way to make a unambiguous decision, because this is basically deductive reasoning, right? Every p-value is associated with the null hypothesis. So to interpret the p-value, we should first inspect the null hypothesis. So we have to first see what is the null hypothesis, then only we can make inferences about the p-value. Another important point is that the correlation neither imply nor prove the causation. So many scientists and people who are unaware of this silly mistake still makes these mistakes quite often. So the correlation means it is actually the variables are, one variable is causing the effect, because there is a correlation between the two factors. So it is totally incorrect. That is what we have seen that as a statistical confounding. So confounding is a problem in multiple regression as well. A missing variable, also known as lurking variable, might affect both dependent and independent variables. So it is not just for the correlation but also for the regression. This is a very important problem. True confidence interval is often wider and the p-values are larger than what we get, as our samples are most probably not 100% random. So in the real sciences, 100% random sample to get is an impossible challenge or task. So that is why the real p-value is much higher basically, whatever the reporter, don't take it at the face value. Many biological distributions are non-Gaussian and these are not abnormal. So if the population or the sample comes from the population which are not Gaussian, that doesn't mean that it is really abnormal distribution. Many people go straight away for non-parametric tests. So that is incorrect procedure. Mind that all models are wrong. Some may be useful though. So there is nothing like perfect model. All models are wrong, but some are actually better than the others. Don't take precision as proxy for the accuracy. So if you're finding like 0.0001 as it's only the number of significant digits in the measurement is called the precision. That is not same as accuracy. Accuracy is the difference between the real value and the measured value. All statistical tests are based on assumptions. So there are a set of assumptions before performing the statistical test. So if some of the assumptions are invalidated or if they are violated, results from the test doesn't make any sense. So you have to be very wary what are the assumptions before performing a test. Statistical conclusions are always presented in terms of probability. So that is why there is the goodness of the probability. So it quantifies the uncertainty. So statistical conclusions that seem 100% definitive are spurious. So don't believe it. If somebody is claiming that because it's significant, statistically significant, the conclusions are like axiomatic, that is incorrect way to to present your data. Negative results are oftentimes not published, that is fact. Most of the publications are positive results only. The negative, if you submit to a good journal, they will not accept it. So that is called publication bias or positivity bias. Most of the published statistics are biased and unreproducible. That is also a fact. A vast majority are false positive. That is called publication bias. So false positive results are being published. Among true positives, results with maximum effect size are often cherry picked. So minimal effect size are not taken. Mostly the effect size or if you are comparing the means of the two groups, very large differences are only taken preferentially. That is called cherry picking. That is also a big problem, the logical fallacy that we have covered in the first module. So this is what you call as winner's curse. So this fallacy is what you call the winner's curse, because that the cherry picking the maximum effect size. P-hacking is also very common. Gotcha in 2006 paper, they found that the vast majority of published p-values are slightly below 0.05, presumably through the p-hacking. So if the value is the borderline little bit less than 0.05, that definitely means that there is some p-hacking going on there. So if the p-value is borderline, highlight this and conclude that statistical significance is only borderline. Many scientists do not do that. If the p-value is 0.04, they simply conclude that it's less than 0.05 and the result is significant. That is incorrect. Thank you for watching this subsection. Let's go to the final subsection of this module.